Okay, welcome back, everyone. Our next presenters are Gaetan Rivet and Salem Saul, and they'll be telling us about OVS DOCA CT Offloads.
Hi, everyone. I'm Gaetan Rivet. I'm a software engineer at NVIDIA. And Salem and I are working in the team who are implementing acceleration for OVS, previously user space OVS, and now OVS DOCA. So today what I would like to talk about was the shift in implementation of CT offload, so the changes that were required to adopt a new approach with offloading. So I will first briefly provide a motivation and general overview about CT offloads, then some implementation details, and then I will leave the floor to Salem to provide the testing description and then the results that we got. Okay, so connection tracking offload. In general, connection tracking are used to implement access control and security groups in OVN. So as a result, there is a lot of traffic that will go through ConTrack in OVN and cloud deployments. So considering that if we do not offload it, that means we have to use the CPU for it. It becomes a quite heavy cost. For our customers who wanted to use OVS DPDK for generally operational reasons, it was not acceptable. And so we were required to implement it and to provide that. So connection tracking in general is, when we try to offload it, that means we build up a simplified representation of connection tracking. So we have to select where we want to simplify and what is the most relevant to execute in hardware. The idea is that we will keep all the remaining complexity in software, while in hardware we will keep only the very simplified version. So to start with, we only offload UDP and TCP protocols. We also do not support fragmented packets. We do not support reassembly. We will only do that in software. Also, we only offload validated connections, meaning that we are waiting for the remote endpoint to confirm that it is actually interested in having this connection. So for UDP, we wait to reach the state where we have bidirectional traffic. And then for TCP, that means we wait for it to be established. There are additional simplifications, which is first that we are only doing a limited TCP window validation. It is actually only executed on the opening sequence of the TCP connection. And then once the offload has been installed in hardware, it is bypassed. And finally, we only support a subset of the CT metadata. So in particular here, you can see that the CT label is reduced from 128 bits. We only support 32 of it. So for our customers so far, it was sufficient. But of course, it depends on future OVN use. So as a result, the hardware rule that implements this CT offload has a match that is roughly the same as the software ConTrack key, except that all the ICMP related fields are removed. And then, the action is pretty much exactly the same. Now, considering that we have selected the state for which an offload exists in hardware, we can execute a much simplified TCP state machine. So we rely on the software to execute the opening sequence. And then upon receiving the SYN-ACK packet, we actually install the hardware rule. And while in hardware, we simply process or match on the TCP flags to verify that it is still valid to remain in hardware. And so as long as we have only data packets, then it will stay there. And once we receive a fin or a reset segment, then we enter the closing sequence. So what it means in the end is that we do have to pass the TCP flags at some point in the CT context in hardware. And the closing sequence, once executed in software, will trigger the removal of the hardware entry. Now, in a more concrete terms, what exactly does it mean to have an offload rule, a CT offload rule, compared to the megaflow, the more generic and more powerful megaflow offloads? So to start from a megaflow that has a CT action, megaflow can be split in two parts, the match and the list of actions. And here, if you have among the actions of that megaflow, you have a CT action. We will then split it in three parts, what we call the pre-CT part, the CT, and then the post-CT. So in the pre-CT part, we keep all the complexity of the match for that megaflow. There are no modifications to it. Then we take only the actions that precedes the CT action to build up the pre-CT offload rule, onto which we add two actions, marking the packet with an ID. That ID identifies from which megaflow we started from, and then we jump to the CT context. In the CT context, we have only 6 tuple match, so five tuple for CT and then CT zone. We write down some metadata. On top of that, if it was CT NAT, then there are NAT actions. And then if we have a hit in that CT context, we move on to post-CT. In post-CT, we do the match only on the mark that was previously written to the packet. And then we finalize with the rest of the actions that were not previously used. So as a result, I mean, those actions can be anything. You could, for example, recirculate, jump to a port, jump to another table, whatever. So there are no limitations. What I want to explain there is that the complexity of the megaflow tables and the megaflow context are only relevant and only used in the pre-CT and post-CT parts, while actually the CT rule itself is very simple. It is small, regular, always the same. It's 6 tuple match plus a few actions. And additionally, the scale of each of those steps is very different. In the megaflow context, you will usually have in the thousands of rules, while actually in the CT context, you have the order of millions of entries. So we had the first implementation years ago, which was based on the same infrastructure that was used for megaflow offloads. So previously, the megaflows were synchronized from the data path classifier directly. And you go into the hardware offload thread, where then you insert them in the hardware classifier exactly as they are. So on top of that, in the contract module that executes in the user space data path, you take the state of each of those objects, and then you send them to the hardware offload thread to finally insert them in a new contract context there in the hardware classifier. And in order, I mean, there you reuse exactly the same infrastructure, the same logic as megaflow offloads. So the only difference is that you have much higher scale and much more important needs than which actually the data infrastructure was not scaled for. So we tried to improve it as much as possible. We made it concurrent. We made a hardware offload thread pool. After the parallelism, we tried to simplify and reduce as much as possible all the work that was needed. But okay, so for now, we lived with that kind of approach. And the benefits was that we will reuse exactly the same API as the mega flow offload logic. There are functional issues with this approach, with the asynchronous operations. For the TCP deletion, you can have a race condition that appears. For example, when you start the closing sequence in the TCP connection, you expect to have a NAC segment for first FIN segment. And sometimes that ACK segment will have no other flags. And as a result, I mean, it could be considered as a data packet, considering the very simple match on the TCP flags that are expressed in the CT offload. And so if your asynchronous deletion is backed up by too many entries and too much volume of work to do, then you could just process that last ACK entirely in hardware. And as a result, you will get an incorrect TCP state machine in software. So you have workarounds for it, but it's just not very clean, generally. So to recap, we first used the RT Flow API from DPDK. It is a very flexible, very simple, in a sense, to use API. It does dynamic allocations. It does just very powerful description of the flow representation. And also it reuses an existing infrastructure. So of course, it's much faster to implement, much faster to adopt. However, there are issues with it. The volume is just not the same at all. It's not scaled up for it. And we have functional issues. Now, the connections, the hardware offloads for CT are very simple, small, very regular. So the question then becomes, why do we reuse the same representation? Additionally, I want to stress a point, which is that offloading is not an end of itself. It's only meant to accelerate, and it's an overhead. So if that overhead is too costly, then the acceleration is nil. You are actually just losing cycles, losing memory to do this offloading. And depending on the kind of connections that you offload, then actually it could be a net loss. For example, you could have very, very short connections with the data that is embedded with the FIN segment. And as a result, you will have absolutely zero packets processed in the hardware for the TCP connection. So that's an issue. If you cannot increase, I mean, in the future, we plan that, but if you cannot, for now, increase the number of packets that will be processed by the hardware offload, then the only alternative is then to reduce the cost, to reduce the overhead of the offloading process. So we have to kind of shift in perspective, get back to kind of basic approach, where, in a sense, interpreting the several layers of abstraction about what the user wants to do with its network is part of the control path. We have to interpret those configuration and those executions to build up the nodes of the packet processing graph, while actually synchronizing the state that is required for correct execution of a single flow action needs to be part of the fastpass. It needs to be part of processing the packet itself. And so, well, we had this issue on our side for OVS DPDK, OVS user space, but it's actually much larger than that. We had the hardware, we have NVIDIA, Mellanox hardware that we know is capable of much, much more than that. And we are constrained by this approach, this architecture. So we came up with a new framework called DOCA, which has been released. And the purpose of this framework is to try to make the best of our hardware. It is developed and architected for now with one guiding principle, which is that we try to make everything or do everything that is necessary to reach the fastest possible execution in that computation medium. So that's what we call the speed of light. As a result, you have a framework that changes a bit the things from, for example, DPDK APIs. You have a template-based API. You do not use a TLV representation, which is very flexible and can be compatible with many vendors, but requires complex translations internally. You pre-allocate everything. You have pools of match actions, offload resources. Also, you have a cooperative thread model where you will use distributed data structures where all of the threads will participate in modifying the internals of those data structures for resizing and destroying. As a result, you end up with a framework that does absolutely no locking and very little atomic synchronization between the threads. But what does it mean when you try to adopt this framework in the user space data path? Well, we had to change a few things. First, in the polling threads, the actual processing of the packet now becomes part of the offloading process. So we want to register those polling threads as also offload threads. So you have a slightly more dynamic offload thread pool. Then you have those threads, they need to participate in the upkeep of the distributed structures that you will use inside of Doca. And finally, we had to make those polling threads static because Doca expects all of the registered threads that will work on their own internal structures to remain for the whole lifetime of the process. Additionally, we started from a previous implementation of contract offload, which was based on RTE flow. That had to be rewritten almost entirely on the whole vertical. So now we started to pre-allocate absolutely everything. We have static size. We batch the offloads. Also, we have a much higher scale of number of connections that we will process. So suddenly the aging thread for the connections in software is not capable of handling all of that. Additionally, as you further and further vertically integrate your offloading process, then you have some opportunities and new capabilities that starts to appear. So for example, here for plain city, what I call plain city is anything that is not CityNat. You have some very regular, very low variance in the actions that are applied. So you can actually share them between a lot of offload entries. So you reduce the allocations of such actions, and you have a faster insertion and faster packet processing in hardware because the hardware then has to only reference a single action. Finally, in Doca flow library appear the type of table, a city table, which is dedicated only to doing contract in hardware. And as a result, they can implement that logic in the absolutely smallest and simplest form possible for our hardware. So it provides the best possible performance. We cannot do that with any other kind of abstraction, higher level abstraction in DPDK. So now that we move back the offloading process in the polling thread, we have a direct access to that specific context in the hardware. So you keep the same asynchronous approach for the Megaflow, because in the Megaflow, you are still building up a complex topology to describe those matches. But in the PMD thread, considering that you can be very fast, you can simply directly write it, so synchronous approach, and you simply have a kind of island of low complexity in your hardware classifier, which is dedicated to only contract offload. So to recap, the complexity that is required for flow offloads is actually not necessary for CT. Considering the constraints and the requirements to do contract offload, it's actually an added overhead that is completely useless and also more fragile in terms of functionalities. And also, with that overhead comes the need for any user that considers maybe deploying that to do a careful analysis of the distribution of sizes in its contract. So that analysis is always slowing down people to make sure that they actually want to make this effort. Coming back to first principle, we find the need for a separate approach, and then we were able to do the effort of adopting it in the user space OVS. However, The issue with that is that it has a wide-reaching impact. So it modifies a lot of the threading model, a lot of how the threads are working, and the polling threads well, the duties are slightly different. Also, the work is in progress. So we had already first results there and a first version that is out. But as we see the vertical integration progressing, we see more and more perspective there, more and more possibilities to accelerate further the software data path being helped by the hardware data path. So it's kind of more integrated approach, and that's coming in the future. So I will then let Salem to describe to you how we want to test the performance of those contract offload, and then provide the results.
Okay. So I'll start by going over our test topology, what we have. So we have two identical physical nodes, each running Oven 2409.1, running a 96-core AMD CPU. Only one physical core of those were given to OVS. And our traffic generator was Keysight SciPerf. And in short, like SciPerf is a cloud-native application which simulates real-world heavy load traffic, which allows us to test the scalability and the performance of the setup of our system. Our NIC was NVIDIA's Connectix 7, 200 gigabit Ethernet dual port, and we set the MTU as 9,000. So on our physical setups, we have a VM per setup, which has a VF attached to it. And using Oven, we configured two local switches. One of them was connected to OVS via local net port, and both nodes are connected together using a logical router. One VM is a client, the other is a server, and logically the packets from the client to the server and vice versa, they go through this path, but physically they go to the local switch, do SNAT and DNAT, go and reach the other side, and the other side there's also NAT and DNAT. So for our testing, the first test we did was we wanted to identify the maximum number of concurrent connections that we can, the maximum number of connection insertion rate that we can hold in a system without having any drops. And we wanted to simulate real-world scenarios which connections are opened and closed all the time. And we focused on HTTP application traffic. We measured the throughput and the connection establishment rate. And basically what the test does is we generate the number of HTTP traffic, attempt to initiate a connection with the SciPerf server. Once a connection is established, we send a GET request to the server with session size bytes, wait for the reply. If everything was successful, send a POST request, also of session size bytes. This session size is what will vary between our two test case scenarios for the CPS. Close the connection, loop over this sequence for a defined target of connections per second for 10 minutes. If SciPerf identifies like drops or TCP retries, it scales down the defined number of CPS in order to keep the system at a stable rate with no drops whatsoever. And we split this test case into two. The first one we called the long connections, where this is our favorable case because most of our traffic is offloaded and the hardware acceleration kicks in. In this case, our session size was 850 kilobytes, and we'll look at the numbers now. So here we see that OVS DPDK is capped at around 150 gigabits per second throughout the whole test, while OVS DOCA is 2.5 times better than it in terms of throughput, reaching a line rate of almost 400 gigabytes throughout the whole 10 minutes. We can see the same sequence also in connection rate, which is the rate of opening and closing of connections. OVS DPDK is capped at around 12,000 connections per second, while OVS DOCA is also 2.5 times better than it at around 28K. This makes us think that we have the same resources. Only one core was given to both OVSs, and with OVS DOCA, we have 2 times better performance. So this leads us to the question, how many cores do we need in OVS DPDK in order to reach the same numbers as in OVS DOCA? So we tried to scale up the PMD threads and the number of RxQs per port. And the best numbers that we could get was with 32 cores attached to OVS DPDK. each core handling only a single queue. The CPUs were isolated. And here we got around 250 gigabits for OVS DPDK, scaled up to 32 cores. Still, OVS DOCA outperforms it by 1.5 times in terms of throughput and also connection rate. Now, this was our favorable case, so we thought, okay, how does offload affect the software processing performances here? The CPU is not doing anything. So for that, we revised the test a little bit, in which we emphasized opening and closing on connections with not so many packets offloaded. Here, our session size was 2 kilobytes, and per connection, there was only around 3 packets offloaded. So here we see that OVS DOCA and OVS DPDK performs the same, where most of our packets is not offloaded. So our software slow path is identical. So we know that the offload handling part of OVS DOCA is not affecting the software performance at all, both in terms of throughput and in terms of connection rate. Now, for the second test that we wanted to do was we wanted to evaluate or find out how many concurrent connections that we can hold in a system and keep them open at the same time. For this, we had the concurrent users test, which we measured the connections rate and the number of concurrent connections in a system. So what this test does is we'll just attempt to open a defined number of connections, keep them open for 10 minutes for our case, and see if there are drops or not. And if there are drops, the connection will be attempted to reopen. And what we got here was that with OVS DOCA, we reached the 1 million mark. OVS DPDK reached it as well. But a small disclaimer here, though the graph is showing overlapped lines and both of them are pointing to the 1 million, OVS DPDK never really reached the 1 million. It's just because our units here are very small, and trying to show you the small fluctuations would result in a very ugly graph. We have the CSV files, though, if anyone wants to review them later. We see that OVS DOCA reaches the 1 million faster, and this is also demonstrated by our connection rate. Here we measure the number of opened connections per second, and we see that once the 1 million are reached, OVS DOCA completely maintains a flat line, meaning that we can hold the 1 million connections open at the same time, and no packets are offloaded whatsoever. No packets are dropped whatsoever. And in OVS DOCA, in OVS DPDK, we have drops of packets. So OVS DPDK can process all of the packets from the 1 million connections. That's why we see this line that never reaches flat. All the time it tries to open the connections again because of TCP retries. So what can we conclude from this? We know that OVS DOCA now is a must if we want to reach 400 gigabits per second. It provides us better performance for less resources. It has no effect whatsoever on slow path, which is a very credible solution for clouds where most of our connections are short. And the best part is that this is only the beginning. We still have much more optimizations to do and better numbers to reach. Thank you.
Thanks. Do we have any questions in the room or online?
Oh, hi. So you mentioned the TCP flags processing hardware. How do you handle invalid traffic? Like if you are getting like a scene packet in the middle of connection, is it just going to be processed in user space or in hardware?
Yes. Any control flag, such as a scene segment, will get sent to the software process.
Okay, thank you.
You mentioned in the beginning the limitation about CT label being 32-bit.
I'm sorry, I can't hear
You mentioned in the beginning the limitation about CT label being 32-bit long for offload. Does that still apply to DOCA or?
Yeah, so we have a limited space available in the hardware to write down metadata. So we have two approaches there. First, we can either write down only the 32 low bits of the CT label, or we can do a mapping actually we take the full word that should be written to the 128 bits of city label, and we map it to a lower ID. Then we try to retrieve it later. So it's two different approaches, but for now, the preferable approach is direct writing the 32 low bits.
Okay, and if I remember correctly, there was another limitation in the past about masked matches on city label. Is that still the case?
I don't recall that. No, I can't tell you.
It's okay. Thanks.
Any other questions? Okay, looks like we have some online. This is from Newman Sadiq, and he asks, does OVS DOCA also have CT state match limitations?
So, well, we support the full width of the city states. However, we restrict the offload entries that will get inserted to only, well, first the one that have established, so established bit plus, of course, the tracked bit because it's implied. Otherwise, no. For example, all the other states are directly taken from the software entry. So, for example, DNAT or SNAT bits are copied as is.
Thanks. It looks like Ellie in the chat also wrote that the limitation of masked match applies only if using the mapping approach. I think that's for Dimitru. Okay. Any other questions? No? All right. Let's thank our speakers. Thanks.